welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 6, Lesson 2, solving one-step equations with addition and subtraction. So in the last lesson, we looked at maybe the two most important ideas in all of algebra. One, the idea of an equation being just a statement about whether or not two expressions are equal to each other or not. And two, what it means to have a solution to an equation, i.e. a value of a variable that makes the equation true. All right? Now, what we haven't done yet, but we're going to start today, is how we actually go about finding the solutions to equations. So let's jump right into it in the first exercise. All right, here we go. Solving equations. To solve an equation means to find all solutions to the equation. In other words, to find all the values of the variable that make the equations true. Now in exercise 1, it asks us for each of the following, state whether the value of the variable solves the equation and justify. All right, so this isn't, how do we find solutions? This is again just, are these values that are supplied, x equals 7 here, a equals 1/4 there, are they solutions to these equations? So since this was primarily what you did on the homework in the last lesson, pause the video now and see if the values that are supplied here are solutions to these equations. Take a moment. All right, well here we go. It's simple enough, right? All we're going to do is we're going to take our 7 in the first equation, right? We're going to substitute it in for x. We're going to have 7 plus 3 is equal to 8. 10 is equal to 8. That's false. And so the answer is no, that's not a solution. Now, of course, a little more difficult because fractions always make our lives more difficult. We're going to take 1/4 as the value of a. We're going to substitute it into this equation and we're going to ask ourselves, is 1/4 plus 1/2 equal to 3/4? For some of you, it's probably immediately obvious that the answer is yes, but of course to add two fractions, we want to get a common denominator. So we can change our 1/2 into 2/4, and then of course 1/4 plus 2/4 is 3/4. 3/4 is equal to 3/4. Since that is true, the answer is yes. That is a solution to this equation. Now again, what we have not done yet is talk about how we can take an equation and produce values that are solutions. That is one of the primary objectives of algebra, which is, here's an equation, what techniques can we use to find its solutions? Let's start to get at that idea in exercise number 2. All right, so here we go. I love using scales as an analogy for equations. So let's take a look at exercise 2. The balanced scale below shows a representation of the equation in exercise 1a, with x being an unknown number of blocks on the left-hand side. Letter A says the equation will only be true if if the scale is balanced. Why does this make sense? All right, so let's talk about this. Right, we can really think about a balanced scale, if you've ever used one in science class, as saying, hey look, the scale will be balanced if the weight on this side is equal to the weight on that side. And why does that make sense? Just because of that reason. The two weights must be equal to balance. And let's color that in a little bit. So just to keep in mind, right, what we're saying here is that this model of a scale is equivalent to this equation that we looked at in letter A, right? I've got x plus 3 blocks is equal to 8 blocks, and I'm trying to figure out how many blocks x represents, right? So let's take a look at letter B. In order to have the variable x by itself, isolated on the left-hand side of the equation, what would we need to do to the scale? So let's talk about this big time. All right, in order to solve an equation, what we almost always do is we isolate the variable. Isolate means to be by oneself, correct? Right? Think about that term, to isolate. You'll hear that a lot in algebra. Right now, x is on this side of the scale along with 3 blocks, but I want the x to be all by itself. So it's really easy. In order to isolate the x on the left-hand side of the scale, we'd have to remove 3 blocks. Literally. We'd have to come up here and we'd have to go, all right, I'm going to get rid of this block, and this block. Okay? Now, very important, I'm going to try to keep the picture in here while having letter C. Letter C asks us, to keep the scale balanced, what would we need to do to the right-hand side of the equation? Show both by crossing off the blocks in the model. All right. In other words, the scale will only be balanced if we have the right value for x. But if I want to get x by itself, I got to take these 3 blocks and throw them off the scale. But as soon as I took those 3 blocks and throw them off the scale is going to be out of balance. Unless I also remove 3 blocks from the right. And our mysterious red pen rears its ugly head again. There we go. Also remove 3 blocks from the right-hand side. That's easy enough to do. But what's great about that then is it tells me exactly what x must be, because x is all by itself on this side, and what we have left on this side is 5 blocks. So if they are to balance, then x must equal those 5 blocks that remain. Now that has a direct analogy in how we solve the equation, right? Because we don't want to have to draw a scale every time. Right? When we have this equation in letter D, which says solve the equation by going through the same steps on the equation, show your work, then what we're really doing is we're really taking this equation, x plus 3, and we're subtracting 3 from both sides of the equation. All right? Now obviously 3 minus 3 wipes itself out, right? That's just 0. We can literally kind of cancel these out, leaving us only that x on the left-hand side. On the right-hand side, then, we have 8 minus 3, and we just get 5. All right? And this brings us to an immensely important idea, right? When I look at an equation, if I'm trying to isolate the variable, I think to myself, well, what's been done to the variable? All right? 3 has been added to the variable. Well, if I don't want that 3 added to the variable anymore, I have to subtract 3 to get rid of it. But if I subtract 3 from the left-hand side, I must do it to the right-hand side or the scale gets out of balance, right? The golden rule of algebra, what you do to one side of the equation, you must do to the other side. So if I subtract 3 from the left-hand side, I must subtract 3 also from the right-hand side. Let's get some practice on that in the next exercise. So to solve an equation, we can simply subtract the same amount from both sides of the equation, assuming something's been added to x. So let's look at exercise number 3. Solve each of the following equations using subtraction. Show your work. All right, great. So this is the easiest thing on earth. I'm gonna rewrite the equation right here just so it's a little bit bigger. N plus 8 is equal to 19. Now again, think about that scale, right? I've got n and another 8 blocks is equal to 19 blocks, right? So I've had 8 added to n. Now I could rewrite it as n plus 8 minus 8 equals 19 minus 8. But very often to save room, what we'll do is we'll do something like this. It literally almost looks like it's a subtraction problem. And then what we do is we just say, well, 8 minus 8 is 0, right? 8 minus 8 is equal to 0. And you could definitely write this down, right? N plus 0 is equal to 11. But of course, n plus 0 would just be n. I mean, if I have n and I add 0 to it, I just have n. So many people will skip that step and they'll just say, all right, well, these two cancel because 8 minus 8 is 0, so I simply have n equals 11. But that's all there is to it. If I have c plus 42 equals 97, and again, let me write that out larger. If I've got c plus 42 is equal to 97, I can subtract a 42 from both sides, right? That will leave me with only c here, and then 97 minus 42 is 55. Don't forget, of course, that you have the ability to figure out whether or not your answer is right or wrong simply by taking this value, putting it back into the equation, and seeing if it makes the equation true. Oftentimes, math teachers will call that a check, a check on your answer. And certainly, it makes a lot of sense to just do that kind of almost in your head. Oh, I got 11 here. Is 11 plus 8 equal to 19? Yeah. Here I got 55, a little bit more difficult. Is 55 plus 42 equal to 97? Yeah, right? Now, letter C, fractions, right? Fractions, fractions, fractions. But still, it still works the same way. If I have x plus 1/3 is equal to 5/6, then I have to subtract 1/3 from both sides. And yeah, that's kind of obnoxious, right? Because I've got to figure out what 5/6 minus 1/3 is, but, right, as long as I can get a common denominator, and that common denominator would be 6, right? So I can change 1/3 into 2/6, then I'll get 5/6 minus 2/6 is 3/6, and I should probably simplify that so x is equal to 1/2. All right, and I know fractions make your life more difficult, but this is a good situation where we can say, hey, look, whether they're whole numbers or they're fractions or they're decimals even, and we'll spend an entire day on messy equations, but no matter what they are, we should be able to still go through these procedures. Now again, keep in mind that every time, I should be looking at this thing and saying, well, I've added 8 to n, so I'm going to subtract 8 in order to get n all by itself. I've added 42 to c, so I'm going to subtract 42 from both sides to get c all by itself, and with this obnoxious fraction. All right. Now, algebra is always kind of been invented, or has always been invented, in order to solve problems, and not just these kind of problems, but like actual problems in the real world. So we're going to be doing some very light algebraic modeling as we go through these equation techniques, and we'll see some of that in the next exercise. So let's take a look. Exercise number 4. Samantha has 22 tickets for the fair. Samantha has 8 tickets more than Mia. Let the variable m represent the number of tickets Mia has. Write an equation involving m that can be used to find the number of tickets Mia has, then solve it. Now, let's be very clear, okay? You don't need algebra to solve this problem. You just need to be able to read carefully. But let's take a look at how the algebraic modeling process works, right? So m is the number of tickets Mia has. We know that. We also know that Samantha has 8 tickets more than Mia. We know that, right? So that means that m plus 8 must equal the number of tickets Samantha has, right? I mean, again, if Mia has 2 tickets and Samantha has 8 more, then Samantha will have 2 plus 8, or 10 tickets, right? So that's simple enough. If m represents the number of tickets Mia has, and Samantha has 8 tickets more than Mia, then they must have m plus 8 tickets. All right, but we're also told that Samantha has 22 tickets. So if m plus 8 equals the number of tickets Samantha has, and Samantha has 22 tickets, then m plus 8 must be equal to 22. And this equation, this very simple equation, really models what we're told in the problem, right? We're told m is the number of tickets Mia has. We're told that 22 is the number of tickets Samantha has, and that Samantha has 8 tickets more than Mia. So I set the number of tickets Samantha has in terms of m equal to how many we know, 22. And now, of course, to solve this equation, we do what we did in exercise 3. We're going to subtract 8 from both sides. That's going to isolate the m. 22 minus 8 is 14, so Mia must have 14 tickets. Now again, I want to be very clear. You could have easily been given this problem back in 2nd grade, right? Samantha has 22 tickets, right? She has 8 tickets more than Mia. How many does Mia have? Oh, 22 minus 8, Mia has 14 tickets, right? Should have been able to easily do that with subtraction way back when, maybe even earlier than 2nd grade, I don't know. But what we want to see is how the algebraic process really kind of mimics what we would already do with arithmetic, because that's the idea of algebra. The whole idea of algebra is using what we can already do with arithmetic on equations that involve numbers that we don't know. All right, let's keep going and doing a little bit more with these one-step equations. Now, to solve equations using addition, right? So before we were solving equations by using subtraction, but let's take a look at one where we use addition to solve an equation. Exercise number 5. Nathan has an unknown number of cookies. Okay, so we don't know how many cookies Nathan has. He gave 4 away and was left with only 2. This can be modeled with the equation n minus 4 equals 2. All right, so let's talk about that for a minute. Obviously, in this case, n represents how many cookies Nathan has. He gives 4 away, so that's indicated by subtraction. And what he has left, that's equal to 2 cookies. All right, so this equation, n minus 4, models the information we're told in the problem, assuming that n is the number of cookies that Nathan starts with. Letter A asks us, what is the solution to this equation? Use common sense. Pause the video now and write down what the value of n is. All right, well, obviously, n is equal to 6, right? So, you know, we can figure that out either by just saying, well, let's see, Nathan started with how many cookies, then subtracted 4 and ended up having only 2. Well, Nathan must have started with 6. Or we can even just look at this equation and say, well, what number minus 4 would equal 2? That would be equal to 6. But what can we do to just actually figure it out from here? Well, that's letter B, right? Letter B asks us, what can you do to both sides of this equation in order to get the answer to A? Show in the equation below. Well, what we can do is kind of almost the opposite of what we have been doing, which is because now we've subtracted 4 from n, I can add 4 back to both sides, right? So literally, I want to do the opposite of what's been done to the variable. So instead of now subtracting 4, I will add 4, and those will cancel out, and I'll get 6. One of the biggest ideas in algebra is to isolate the variable. We should do to both sides of the equation the opposite of what has been done to the variable. So in the first set of exercises, we kept adding numbers to the variable. So to undo that, to get the variable by itself, we subtracted. In this case, we subtracted 4 from n to get 2. So to get n all by itself, we now add 4 to both sides, and we get n equals 6. We can think about this. Subtracting 4 and adding 4 is canceling each other out. You know, if I had 10 bucks in my wallet and I paid $4 to somebody and then somebody gave me $4 back, right, minus 4 plus 4, I'd end back at $10. And that's the same idea here. If I've got, 6 cookies and I take away 4 of them and I'm left with 2 and then I give 4 back, then I'm back to where I started, which was 6. So let's get a little practice on this in the last set of exercises. Real simple. Exercise number 6. Solve each of the following equations using addition. Show your work. Again, what we want to do is we want to look at this kind of equation. We want to say, all right, I've got x minus 10 is equal to 17. In order to have just x on that side, I'm going to add 10 to both sides, right? And then that subtraction by 10 and that addition by 10 will cancel. I'll then have 17 plus 10, and I'll get 27. And again, should make all the sense in the world, right? I could check it. I could say, okay, 27 minus 10 equals 17. 17 equals 17. Yes, that's true, so that's the solution to the equation. Why don't you take a moment and solve letter B and letter C on your own, and then we'll go through them. All right, easy enough. Here we go. Right, I've got d minus 26 is equal to 54. Right, in order to undo subtracting 26 from both sides of the equation, I'm going to add 26. Those will cancel, those two operations that is. Then 54 plus 26 is going to be 80. Right, the last equation, maybe the easiest one. Right, I've got m minus 7 is equal to 28. In order to undo the subtraction by 7, I'm going to add 7 to both sides. Those two cancel each other. 28 plus 7 is 35. And that's the solution to that equation. All right. Both situations, both the first and the second, are what we refer to as one-step equations because it literally takes a single arithmetic step, i.e. either subtracting a number from both sides in the first case or adding a number to both sides in this case to get our final answer. We're going to be working more with those in the future lessons, but let's wrap this one up. So what we saw today were all kinds of equations where we had like x plus a number equals a number, and we solved that by subtracting whatever was being added to x from both sides. Then we also saw equations where we had something like x minus a number equals a number, and then we had to add back whatever had been taken away from our variable to kind of get it back up to where it was, right? The idea is very simple. Look at the variable, ask yourself what has been done to it, and then you do the opposite to it to get it all by itself. We'll see that more in the next lesson where we look at some multiplication and division involved in solving equations. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.